Okay, so the binomial distribution. I bring this up today because it turns out that it is related to the normal distribution, but we use it for a different purpose. So it's used for any event with two possible outcomes, that is a binary variable. And we use it to describe the number of one of those outcomes in a series of repeated independent events, like 1,000 coin flips. So one event would be, say, does or does not have cancer, or heads or tails. We call that a trial. An example being here, what is the probability? So this is an example of something that you could describe using the binomial distribution. What is the probability that among 100 randomly selected individuals in New York City, 60 of them have private health insurance? So it could be, what's the probability that exactly 60 of them have private health insurance, or the probability that 60 or more of them, or 60 or fewer of them have private health insurance? What's the one other thing you would need to be able to answer this question? Yeah, the probability of an individual in the population having private health insurance. Exactly. So these are actually very important. Maybe you go ahead and circle these in your notes, because you need to know these. Having these handy will prevent you from using the binomial distribution in an inappropriate setting. You can only use it if these three things hold. First, the trial has two possible outcomes, which we will refer to as a success or a failure. A success won't always mean something good happening. It just means that that is what our probability is of. We might use a success to mean having cancer or something like that. It doesn't mean that it's a good thing. It just means that that is the outcome which we are describing the probability of. So two possible outcomes. Second one, that each trial has the same probability of success. That is, these are independent events. So in the example of the coin flip, every one of those coin flips must be independent. And in the example of cancer, these have to be people for whom the probability of one of them having cancer does not depend on whether others around them have cancer. Maybe a better example of where that would be violated would be an infectious disease. If you have a room full of people and one person gets the flu, then suddenly the probability of other people having the flu goes up. And that's not a Bernoulli trial, because those probabilities are not independent. Whereas if it's 30 people spread out on the remote corners of the world, maybe that would be described by a binomial distribution. That one's very important. By the time you're in BIOS610, we'll cover methods for non-independent events that are counts. We use the Poisson distribution, the negative binomial distribution, other distributions besides the binomial distribution. So actually I already covered here the third one, that the trials are independent. The same probability of success, that just means that it's not that, I have a 10% chance, you have a 15% chance, you have a 20% chance. If that's the case, then you won't be able to use the binomial distribution. It's more complicated. All right. So if those things hold, then here is your probability of X successes in N trials. So successes being that the outcome of interest, the number of times that it has happened, so the number of people with diabetes or cancer, or the number of heads that you flipped, that's X in a certain number of N trials. So it's a bit of a cumbersome formula. Y'all remember the factorial? That's like 3 factorials, 3 times 2 times 1. But that's all you have to do. The only catch about this formula, you can program it into a spreadsheet and just use it, or you can use the binom.dist function in Excel. There's also the p binom and q binom in R. The only catch is that once n becomes large, this starts becoming hard to calculate, because if you have 1,000 coin flips, 1,000 factorial is too big a number to calculate on any computer. Maybe not on any computer, probably on any of your computers or mine. But fortunately, there's an approximation that we can use. Here are a few examples. So remember, the normal distribution was described completely by 2 numbers, the mean and the standard deviation. The binomial distribution is also described completely by 2 numbers, n and p, n being the number of trials and p being the probability of a success in each trial. So for n equals 20 and p equals 0.5, this is like flipping a coin 20 times and the number of heads. The mean here is 10. So the most expected number of successes is 10 out of 20. If we were to do 20 coin flips and count the number of heads, and then have every one of you in this room repeat that, most of you, well, more frequently we would observe a 10. And then the next most frequently observed values would be 9 and 11, followed by 8 and 12, and it would fall off. For n equals 100 and probability of 0.5, that's 100 coin flips, and the mean number of successes is 50. And you'll notice that that there's more spread. So when you have only 20 coin flips, the variability, it can only possibly go down to 0 or 20. So that it's not even possible to have a variation of more than 10 from the mean. But when we've got 100, you can have greater variation, and you see that the spread actually is greater. And then one more example here, with n equals 100, but a probability of 0.3. So say this is like a weighted coin that's less likely to come out heads. You see that the width of it looks kind of the same as this one, where the probability of success was 0.5, but the mean is lower. Do anyone want to tell me if these distributions look familiar? What do they look like? Yeah, they do. They look like the normal distribution. And this is going to kind of come to the rescue when we're talking about large n. Here's just an example. I'm going to skip over this. To calculate the probability of 3 out of 4 individuals, so this is a small n being diabetic, you would want to use the binomial distribution, and you could just plug them into that formula and get a probability. If you wanted the probability of either 3 or 4 of them being diabetic, you could do it for 3 and 4 and then add those probabilities. All of these are now, I'm just taking advantage of that rule of summing of probabilities, summing to 1 if they're exhaustive. But so the normal approximation of the binomial distribution. This is what you're going to want to use if you've got large n, because it's easier, and also because it's problematic calculating those factorials. This square root didn't quite come out right. This should extend over that whole thing. So that distribution, or that probability of the number of successes, has a mean. of n times p, so the number of trials times the probability of success in each trial. So the 100 coin flips with the probability of 0.5, the mean is 50. And the standard deviation is this square root of n times p times 1 minus p. So remember when the probability was at 0.5 and n decreased, then like we noticed in that plot, the standard deviation decreased. When n was fixed and p went down, it actually did change. It decreased again, although not as markedly. So here's an example of an application. If you have n equals 1,000 individuals, prevalence of diabetes equal to 0.1. So in this case, the number of trials is 1,000. A success, quote unquote, is having diabetes, and the probability of a success is 0.1. Then the mean is 1,000 times 0.1. The average number of people with diabetes out of a group of 1,000 will be 10. And the standard deviation of that, or if you wanted to calculate probabilities, like the probability of having between 8 and 12 people, you would use this standard deviation. It would be 1,000 times 0.1 times 0.99. And for large numbers, as long as both your expected number of successes and failures are at least 15, it's a very good approximation, this normal approximation. Even if they're less than 15, it's still not bad. But if it's above 15, it's a very accurate approximation. And so if you wanted the probability for 20 trials with a probability of success of 0.5, and you wanted the probability of observing a 5, 6, 7, or 8, using the binomial distribution, you would just calculate those 4 things and add them. If we're using the normal approximation, you would get your z-scores for 4.5 and 8.5 and calculate this area between those two values on your normal distribution after converting them to a z-score. All right, that's all we have for today. We covered normal binomial, some new notation, and as long as you're comfortable with, adding up probabilities from different parts of a distribution and looking up values in a table or calculating them with software and converting back and forth between the z-score and other scores, then you'll be fine for this unit.